Good afternoon, everyone. Welcome to EE340 lab. So today we are going to do experiment 2, which is capacitance and inductance of transmission lines. So our objective is to measure the capacitance per unit length and the inductance per unit length of two transmission lines. So the first one is this one, which is the coaxial cable. So as you can see, it has a central conductor and surrounded by a dielectric, and then you have another conductor. So this is the coaxial cable. Then you have the second one, which is the twin wire. So you have these two conductors, and this is the plastic covering of those two twin wire conductors. Now let's look at the theoretical part. So as you can see, this is the capacitance per unit length, and this is the inductance per unit length of a coaxial cable, and this is for the twin wire transmission lines. And by the way, we are going to derive this in our course. Now what we are going to do is we are going to find the capacitance from experiment, and then we will find the capacitance per unit length experimental, that is just dividing it by the length of dividing the capacitance and the inductance with the length of the wires. Then second part is we are going to find theoretically. So these are the expressions that we are going to use to find it theoretically. And the third one is from the manufacturers. So these are the three comparisons that we are going to do: theoretical, experimental, and from the manufacturer. So first let's start the theoretical one. So in the theoretical one, these are the expressions that we are going to use, and this is called as the characteristic impedance of the transmission line, which is root of L over C. Now as you can see, there are some variables here, A and B, and epsilon, mu. Here also A, H, mu, and epsilon. So for the coaxial cable, the epsilon is nothing but it is the permittivity of this material, and also mu, which is the permeability of this material. Now for this material, if you see here, this is the relative permittivity value, which is 2.3, and because these are all non-magnetic materials, so therefore the relative permeability is 1. And we know it very well, epsilon 0 is the permittivity of the free space, and mu 0 is the permeability of the free space, which are constants. Now we are left with A and B. Similarly, for the transmission line, the epsilon and mu values are these. So again, it's a non-magnetic material, so therefore its mu r is 1. And for the epsilon, we use the relative permittivity as 1, which is air, because mostly the electric and the magnetic field between these two conductors are through air. That's why we put air, because this permittivity is the material between the two conductors. Okay. Then you can find the characteristic impedance root of L over C. So now in the theoretical part, we are required to find A and B for the coaxial cable and A and H for the transmission line. So now let's come here. So this is my twin wire transmission line. And how do we define A? If you see here, A is nothing but it is the radius of this conductor. So ideally the radius of both the conductors should be the same. So for us, what we are going to do is we are going to find the radius of this, and we are going to take 2 to 3 readings and then averaging them. So in this way we will get A. Now to get H, what we are going to do is we are going to first find B2, which is this thickness, okay, and then B1. B1 is the diameter along with this dielectric, which is this one. So this is B1 and this is B2. So once we find B1 and B2, we can use this expression from where we can find H. Got it? Now for the coaxial cable, if you see here, A is the radius of the central conductor. So we will find the diameter of the central conductor, and from where we will find the radius. And B is the radius along with the dielectric material. So which is this one? This is B, the radius along with the dielectric material. So we will find the diameter and then we will find the radius. Okay, so this is the theoretical part. And how are we going to do? If you see here, so I have made this table. This table I prefer, that we don't use. So this will be much easier for us. So this is the table of the twin wire, and this is the table of the coaxial cable. So in the twin wire, as you can see, this is the vernier caliper reading. So where we are measuring the 2A, because we will be measuring the diameter, then we will be measuring B1, then we will be measuring B2, and then we will calculate H. So now how do you measure this A and B1? So we are going to use this vernier caliper. So this is called as a vernier caliper, and your instructor will talk about more in the introduction part of this course, of this experiment, sorry. So this is the vernier caliper. So just a brief explanation. This is called as the vernier scale, and this top one is called as the main scale. So this is the vernier scale and this is the main scale, and it has two jaws, and jaws are movable, as you can see. So what we are going to do is, first I am going to put the twin wire conductor between these jaws, and we are going to take the reading. So if you see here, what we are going to do is, this is the main scale reading. So the main scale reading is 0. So it is 0. So I have written 0. And the vernier count. So the vernier count will be it is almost let me just quickly, it is almost 100. It is almost 50. Yeah, it is almost 50. So this is 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. So it is almost 50. And how to get this vernier scale, your instructor is going to explain that when he takes this experiment. Okay, so this is 50, and you multiply it by vernier count. So the vernier count for this vernier caliper is 0.02. So you will get a value of how much? If I remember correctly, you will get a value of whatever it is. You can write it down. Let me do it. Just give me a second. So it is 1 millimeter. So it is 1 millimeter. Got it? So like this, we are going to take 2 more readings, and we will be focusing on the vernier caliper. And now it's your duty to freeze the frame and then find the main scale reading and the vernier scale, and then multiply it by the vernier count and then find the value. Okay, so now I am changing a little bit. I am using the second conductor now. So I am leaving it for you to do the measurement. So yes, so now it is focused. Yes, so it is focused now. Done. Okay, so you will get the second reading. Now the third reading. Okay, so this is how you are going to do. So you are going to note down those values in this table and then take the average of that. Okay, so now B1. B1 is along with this dielectric. See here? So it is with the dielectric. So this is the first reading that you are going to take. Done. So now I am going to, go and take B1 of the second conductor. Okay, then the third reading. Okay, so these are the three readings that you got for B1, and those three readings you are going to write it here, the main scale and the vernier scale reading, these three readings. Then you will find the value and then you will average it. And as I have mentioned, how are you going to find the value? Is nothing but the main scale reading plus vernier scale reading. So, and this is my vernier count, which is 0.02. So B1 is done. So now let us do for B2. So B2 is this thickness. Yeah, this thickness. Okay, so okay, so this is the first reading. Do
you want to check it this time and write it down?
Third reading. So this is the first reading. This is the second reading. Yeah, and this is the third reading. So the third reading, let's take it down. So what it says, so the main scale is 10 millimeter. So the main scale is 10 millimeter, and now my vernier scale is, okay, it is somewhere here. So 5, 10, 15, 20, 25. So it's probably 30 or 31. So let us take it 30. So it will be 30 multiplied by 0.02. So if you see here, so it will be 30 multiplied by 0.02, and it will be how much? Just give me a second.
0.6.
So it is 10.6 millimeters. Done. So what you are going to do, again, these three values, you are going to average it and that average value of B2 you are going to take. So this will be the average value of B2, this will be the average value of B1, this will be the average value of 2A. And once you know H, for H we do not require this, so nothing, because for H we are going to use this expression, so it is just B2 minus B1. Okay, so 2H is B2 minus B1. So you find that value and write it here. So this is for the twin wire. So similarly, let us do it for the coaxial cable. So for the coaxial cable, so first let us find the diameter of the central conductor. Okay, so like this, and I'm going to keep it here so that you can take this, you can look at the scale. So this is the first reading, so I'm going to move again. This is the second reading, and again. So this is the third reading. So from this you are going to find 2A. So the three readings that we have taken is for this one. So the first reading, second reading, third reading, and the average value. Okay, so now let's find this 2B. So 2B is with the dielectric. So this is the dielectric. Got it? So this is the first reading. Just a second. This is the first reading. Done. So let me move it again. This is the second reading. Okay. Second reading. Yes. And then this is the third reading. Okay. So done. So this is the 2B value, and you are going to note it down here. The first, second, third, and the average value of 2B and the average value of 2A. So these are the measurements that we need to do with the vernier caliper. So now, since you know all these values now from the vernier caliper 2A, 2B, and this 2A, B1, B2, and H value, then we are going to substitute in this theoretical expressions, and then we are going to find the theoretical values, and those theoretical values we are going to write it on this table. So as you can see, this is the table for the coaxial cable and for the twin wire transmission line. This is the inductance, capacitance, and the characteristic impedance, and three different measured value, theoretical value, manufacturer value. Measured, theoretical, manufacturer. Measured, theoretical, manufacturer. Okay? Now what is this? This column is called the length of my cable. Now I have already noted it down for you. For coaxial it is 7.97 meters, and for twin wire it is 8.87 meters. How I got it, how I measured it, it is very straightforward. We are going to take a meter scale, see here, and then we can just physically measure it like this. So in this manner, we just measure it, but we just need to be careful that we have to measure it from here, okay, from the center conductor, like this, 1 meter, and then you continue like this, 2 meters. So if you continue and till the end of your cable you will get the total length of your coaxial cable. And similarly we need to do it for the twin wire in a similar manner. So you will start from here, and this is 1 meter, then this is 2 meters, and so on. Okay, so that will be the length of the cables, and this is how I got it, and this is the values that I have measured. So why we require these values? Because we are going to compare the inductance and capacitance in terms of per length, per unit length. So therefore, inductance we will measure it theoretically per unit length. See, it is capital L over small l, and small l is your length. Okay, and here also inductance per unit length, capacitance per unit length. So this is my length. So what you need to do here to find the C over L and L over L, you got it, the theoretical values. Now you just substitute here. These are the theoretical values, and here also theoretical values. Now let's go to the manufacturer values, and in the manufacturer values we are going to use this lengths. Okay, so let's come here. This is the manufacturer value. So these are the values that we got from the specification sheet of this coaxial cable. So its characteristic impedance is 75 ohms, and its capacitance per unit length, so it is already given in unit length. So it is 68 picofarad per meter, and for twin wire it is 300 ohms and 13.2 picofarad per meter. So these are your manufacturer values of characteristic impedance and C over L. Now how are you going to get the inductance per unit length from the manufacturer value? You can straight away use this expression. So in this expression, your Z0 will be your manufacturer Z0 value, and your capacitance will be the manufacturer capacitance value. So in this way you can get the manufacturer inductance values. Okay, so once you get it for coaxial cable and for the twin wire, you just tabulate here. So this is for the manufacturer. So the manufacturer for coaxial cable, inductance per unit length, capacitance per unit length, and the characteristic impedance. So in this way we have filled the theoretical and the manufacturer. Theoretical and manufacturer, and for even for characteristic impedance, theoretical and manufacturer. Now we are left with only measured one. Now how are we going to measure? So let's come here. So this is the equipment that we are going to use to measure the capacitance and the inductance per unit length of our coaxial cable. So this is called as LCR meter, which can measure the inductance, capacitance as well as resistance. So what we are going to do is we are going to use auto mode, and so this is our first, which is the twin wire. So what are we going to do is we are going to connect this twin wire conductors here. So conductor here, and as you can see, now if you come here, so if you see here, you have frequency, mode and auto. So we do not need to select frequency and mode until and unless you are not in an auto mode. So since we are going to use an auto mode, so in the auto mode these will be automatically selected. So see here, it is already in auto mode because the light is lit, and the value that we are getting is the overall capacitance of the coaxial cable. It is not capacitance per unit length, it is overall. Okay, so what we are doing, if you see here, this is my cable, so which I have stretched it completely. As you can see, it is stretched. Yeah. So completely stretched. Both cables has to be completely stretched. Okay, so let's come. So this is the capacitance, which is in picofarad, but now it is fluctuating. So if any numbers are fluctuating, then I always suggest my students that you try to find the minimum value, try to find the maximum value, and then average them. So that would be the preferred value. Okay, so if you see here, so it's going between 57 and 78. So 57 and 78. Okay, so as you can see, it is fluctuating. So and as I told, the minimum is around 57 and the maximum is around 75. So 57 plus 77 divided by 2. So this is the value that we are going to take. So it is around 67 picofarad, and this value I am going to write here for my twin wire, the measured capacitance. So which this will be 67 picofarad. Okay, now how to measure inductance? For inductance, it's very important, as it is mentioned in the manual, that for inductance the far end of the line should be short circuited. So for capacitance, the far end of the line should be left open. That means both the conductors should be left as it is, open. But for inductance, it has to be shorted. So I'm now going to go to that far end and I'm going to short it. So this is the one, so I'm going to short it. Okay, so if you see here, in the auto, same, I did not do anything. So in the auto, this changed to series, but now it is measuring the resistance. So to measure inductance, we just press this button. So auto will go away and we will see the inductance per unit length. So it is around 16 microhenry. Okay, 16 microhenry. So this value we are going to write here. So it is 16 microhenry. Now let's do it for the coaxial cable. So if you see here, I'm going to now remove this twin wire and then I'm going to put the coaxial cable. So coaxial cable. So now, since its far end is already open, so it will measure the capacitance. So this is the capacitance value. So it is between 527 to 546. So the average will be 527 plus 546. So it will be 536 picofarad. So let me write it down. So it is here. So it is 536 picofarad. And for the inductance, again I will go to the far end and I will short circuit it. Okay, so I have short circuited. Now it was already in auto. As you can see, now it is measuring the resistance. So in order to measure inductance, so let's just press the inductance button. So this is the inductance. So it is around 4.49, 4.48 microhenry. So let us write it down here. So it is 4.48 microhenry. So this is the measured capacitance and inductance value of the coaxial cable, and this is the measured capacitance and inductance of the twin wire. Now what we are going to do in our final table for the measured value, this is inductance per unit length. So since we already have length, so whatever measured value of capacitance that we have got, so divided by the length to get the capacitance per unit length and to get the inductance per unit length. So in a similar way, you fill the measured value of inductance per unit length for both coaxial cable and twin wire, for capacitance, and also for the characteristic impedance. To find the characteristic impedance, we are going to use the same formula, which is this one, Z is equal to root of L over C. But in here, our L and C will be the measured values. Okay, and the last thing is the percentage error, because these are asked in the question and answers. So the percentage error, we are going to find the percentage error with reference to the manufacturer value. So we will find the percentage error of measured by comparing it with manufacturer, which we are going to write here, and then the percentage error of theoretical with respect to the manufacturer value, which we are going to write here. So complete this percentage errors. Okay, so this was our experiment 2. One last comment: whenever we are going to measure the inductance of the coaxial line, the coaxial line has to be as much as possible straight. There should not be any windings. Okay, and there is a question in the experiment that why we do not require, why we don't, why we should not have this windings. So you need to answer that, why it has to be fully stretched. This one, this experiment, this question number 6. So why it should not, so see, so it has to be fully stretched or extended. If it is not fully extended, then what will happen? So it has to be straight and fully stretched. Okay, so this completes your experiment number 2. So you need to fill this 3 tables, 1, 2, and then this 3 tables, and then you have to submit your lab report. Okay, thank you very much.